My name is Justin Kruger. Today I am presenting on the Starling formation flying optical experiment, its design and some initial flight results on behalf of my co-author and supervisor, Professor Simone D'Amico of the Stanford Space Rendezvous Laboratory. Okay. So I'll start off with the motivation behind this work. I'll then introduce the navigation architecture and algorithms that we're applying. I'll go through some of the initial flight results from this experiment and finishing off with a summary. So in terms of motivation, there is a need to be able to determine the orbits of known or unknown cooperative or uncooperative resonant space objects, or RSO. And the question is, how can we navigate multiple RSOs without GPS? There are many contexts in which we have to do this for things like space situational awareness, for on-orbit servicing and debris removal, and things like resilient or deep space navigation. And that means that we have future missions which require new navigation methods, can accommodate multiple spacecraft in a way that's more autonomous and more scalable. Now, one solution, as pictured on the right of the slide here, is angles-only navigation, in which we have cameras on observer spacecraft, which measure the bearing angles to other system members. And navigation then becomes self-contained, and cameras are themselves quite ubiquitous, low size, weight, power, cost sensors. On the other hand, we have somewhat weaker state observability because bearing angles don't give us explicit information to our targets. And we also have to deal with optical visibility constraints. Nevertheless, two prior flight experiments have demonstrated angles-only navigation in orbit. These are Argon in 2012 and Avanti in 2016. And both of these experiments were successful, Argon being ground in the loop, Avanti featuring some more autonomous elements, but they were characterized by some key limitations. First of all, they were for a single observer and single target spacecraft. They relied on maneuvers to help resolve the target range. They relied on a priori relative orbit knowledge to initialize navigation, and also relied on GPS for absolute orbit determination. So really, StarFox, or the Starling Formation Flying Optical Experiments, has been developed by the Stanford Space Rendezvous Laboratory to really try and remove those existing limitations and thus enable new distributed space missions. StarFox now applies to 4 satellites at somewhat larger separations and performs navigation almost entirely autonomously. So I'll now talk a bit about the navigation architecture being applied here. So for StarFox, we apply something called Artemis, or the Absolute and Relative Trajectory Measurement System. So the bottom of the slide here shows kind of a nominal system using Artemis, where it's deployed on one or more cooperative observers to track one or more non-cooperative targets. Some key elements are that it is angles only, so we're using the onboard cameras to collect bearing angles. It's distributed, so different observers might be estimating a subset of the complete system state. It's cooperative, so we have an intersatellite link, or ISL, which observers can optionally use to broadcast and share measurement information with each other. It's autonomous, so requires minimal external information and is miniaturized, so it's suitable for small satellite hardware, such as CubeSats. So each observer is estimating its own 6 absolute orbit elements, as well as the 6 relative orbit elements, or ROE, of each visible target, as well as some optional state components, so things like ballistic coefficients or the clock offsets between different observers. The measurements being used to do that are the bearing angles of each target, as well as the attitude of the sensor, relating that to the inertial reference frame, as well as potentially any bearing angles being broadcast by remote observers over the intersatellite link. So Artemis aims to leverage new algorithms to enable some critical new capabilities for space systems, such as scalability to multi-observer, multi-target systems, detection and tracking of previously unknown targets on orbit, angles-only estimation of relative orbit states without requiring maneuvers, and estimation of absolute orbit states without requiring GPS access, as well as more general applicability to dynamic environments, not just in LEO, but for things like cislunar navigation as well. So this slide kind of shows a very high-level block diagram of Artemis. It's divided into 2 stages here, the initialization of navigation and then the refinement of the state estimate over time. And there are 3 main software algorithms here in different colors. There's image processing, or IMP, in red, batch orbit determination, or BOD, in blue, and sequential orbit determination, or SOD, in green. So now what I want to do is kind of go through each of those three algorithms at a high level so you get a sort of intuitive picture of what they're actually doing as part of Star Fox. So first, let's talk about image processing, where the goal is to produce batches of bearing angles for each visible target using just the sequence of images from the onboard camera or vision-based sensor, and a course estimate of the observer's absolute orbit at one epoch. That's the only a priori information we need. And so the way IMP does this is we start off with the image and we classify objects and compute their bearing angles using some fairly typical algorithms such as centroiding and star identification. And then what we do is we apply multi-hypothesis tracking to look at all the unidentified bearing angles and enumerate and propagate all the tracks we can form from those angles, which might be our unknown targets. So multi-hypothesis tracking, it's quite robust, but it is costly for a spacecraft to do. So what we sort of used to address that is we realized that we actually know quite a lot about how spacecraft should be moving in the reference frame of our observer because of relative orbit dynamics. So we can develop these kind of parametric models of target kinematics and fit those to our various track hypotheses and use that to select the most physically reasonable hypothesis and prune our unlikely tracks for efficiency. And that lets us to converge to the correct hypothesis without actually requiring any target state knowledge. I guess noting that if we have target state knowledge, we can pick out our measurements much more simply. So the next step here is BOD. So we want to compute initial orbit estimates for our targets using those batches of bearing angles from IMP and that course estimate of the observer's orbit. And BOD sort of goes through this process. So let's say we have a batch of bearing angles y across some set of epochs dependent on the state of the system x. So really the problem we have to deal with is that the target range is weakly observable. Basically, the same arc of bearing angles could be a target that's close to the camera with sort of very little relative motion, or a target that's sort of more far away with larger relative motion. So we address this by essentially defining a set of samples of delta lambda, where delta lambda is the relative orbit element most analogous to the range to our target. And so for each delta lambda sample, we have some kind of initial state estimate x. And for each sample, we compute this delta z value, which is the difference between the modeled bearing angles from our state estimate and the measured bearing angles from the camera. And we can use batch least squared to kind of iteratively update our state estimate to minimize that difference. And we end up sort of producing a plot like this one, where on the x-axis we have our delta lambda samples, and on the y-axis we have the measurement residuals. And so we pick basically this output sample that minimizes the difference between our modeled and our measured values, essentially. And so we're kind of exploiting the relative orbit elements here by dividing our state into strongly and weakly observable components. We can also nicely use these converged measurement residuals to actually help us estimate our initial state uncertainty as well. So we've now initialized our system. Now we can refine that state estimate over time using new bearing angles from the camera, as well as any potentially any bearing angles broadcast by other observers over the intersatellite link. So the SOD module has a number of key features which help us out here. So first of all, it's applying an adaptive unscented Kalman filter with nonlinear measurement and dynamics models to help maximize the angles-only observability. And we can do things like exploit the state parametrization to minimize the amount of orbit propagation on board for more efficiency. If we have multiple observers available, we can also apply distributed stereo vision to give a lot more geometric information to the observer for improving estimation capability. To support that, we have a lot of data association algorithms to make sure we're matching the correct measurements between different targets and different observers. And finally, we have a couple of features like adaptive process noise estimation and estimation of auxiliary states such as drag coefficients and sensor biases online to aid the long-term robustness and autonomy of the navigation system. So yeah, that's an overview of how Artemis works. Now I want to get into some flight results from Starling. So Artemis is currently flying as part of the NASA Starling mission, which is managed by NASA Ames. Starling consists of a swarm of 4 6U CubeSats pictured on the right here, and was launched in July last year. And there are 4 onboard experiments advancing the readiness level of some critical swarm technologies. One of them is autonomous navigation with Star Fox. And to do so, Star Fox applies the onboard star trackers and crosslink radios to do absolute and relative navigation for the swarm. So on the left here, you can see the geometry of the swarm in the radial tangential and radial normal planes of one of the spacecraft. So 2 formations were actually used in flight. The first was an in-train formation with relatively little relative motion, and the second was a set of passive safety ellipses with more relative motion. Noting that the swarm here is primarily separated in the tangential or the along track direction by tens of kilometers or hundreds of kilometers. In terms of the general progression of Star Fox experiments, we kind of wanted to explore more and more advanced capabilities as time goes on with these world first demonstrations, starting off with looking at navigation for multiple simultaneous targets, then looking at the autonomous orbit initialization with the BOD system, then looking at the cooperative multi-observer navigation, and then looking at things like angles-only absolute orbit estimation as well. So this video actually gives an example of some flight results here for the second navigation mode, which is looking at the autonomous BOD initialization of navigation, where on the left, you can see the images from the onboard star tracker. The IMP module is classifying the objects it detects. So the yellow objects are identified stars. You can see the spacecraft identified in little green boxes in the center of the image there. So the IMP is doing its kind of independent multi-hypothesis tracking for about 5 hours at the start of this period. And after that period, it passes that batch of measurements to BOD, which produces the initial relative orbit estimate. The BOD range estimate is actually shown in the bottom in the red here. And then at that point, the SOD system starts to use new measurements to refine the state estimate. So the position uncertainty of the target spacecraft is shown in the blue here, in the radial tangential normal frame. And you can kind of see that we have uncertainty as like the blue shaded region and the amount of state error as the blue line. And we start off with a pretty big amount of tangential error, or tangential uncertainty, I should say, because that's kind of the most weakly observable component. That's what we expect, really. But over time, we're able to refine that quite well using new measurements down to a steady state of uncertainty of around 1% of the range to our target, which is pretty in line with pre-flight expectations. And we can actually achieve this even in the presence of pretty significant measurement gaps. So these gray regions are when we're actually getting new image measurements. And there's quite big gaps there, which shows some promise about the overall robustness of the navigation system. So we have another example here of the 4th navigation mode, where in this case, we are doing simultaneous absolute and relative orbit determination using only bearing angles, no GPS. So what actually happens here is in the top left, you can actually see the relative orbit geometry of the swarm, where a black line indicates a measurement occurred between those 2 spacecraft, and they're all sharing these measurements with each other. And so we can use that to actually estimate the absolute orbit of the observer, which is shown in the green here. You can see this position uncertainty starts off as fairly rough on the order of several kilometers, but we are able to refine that over time using our bearing angle measurements without GPS. And we can simultaneously estimate the relative orbit elements of our 2 target spacecraft, noting that because we have the multiple observers as well, our performance is better than a comparable single observer case because we do have a lot more geometric information to work with as part of the system. Okay, so the good thing here is that, Star Fox was able to achieve almost all of its navigation objectives, either in flight or post-processing flight data on the ground. And all of these were the first time these capabilities had been demonstrated in flight. But many unexpected issues were also encountered, which is the sort of the last thing I want to talk about today. So, for example, our targets were a lot dimmer than expected, and there was a lot more image noise than expected, which made targets overall very difficult to detect. There were errors in the measurement timestamps, which caused biases in the state estimates, and some inconsistent image data transfers, which meant we had those very long measurement gaps that I mentioned. And I think a lot of this could have been solved pre-launch or maybe mitigated pre-launch if we'd had better sensor emulation for our cameras during integration and testing. if we'd also had some more realistic image simulation capabilities to really stress test the algorithms, and with a better understanding as well as of how those time tags for images were being synchronized. Still, the fact that we did have so much success was due to a few factors. I think that we had a lot of tuning parameters to the algorithms, and we had a fairly robust software design to make things adaptable to different anomalies, as well as a digital twin of the system on the ground that we could pass flight data through and use that for very efficient troubleshooting and diagnosing of any issues. Okay, so to finish off with a quick summary here, Artemis enables autonomous angles-only orbit determination for varying multi-agent configurations and has been verified during initial Starling experiments this year. These are the first demonstrations of autonomous vision-based swarm navigation in flights, which provides lots of valuable lessons learned, as well as the chance for an extended mission next year with expanded algorithms. And also, many other research directions are being explored, including support for cislunar navigation, support for rendezvous proximity operations at close range, integration with complete GNC pipelines with control in the loop, and also looking at more space situational awareness applications, such as the identification of transient objects in the field of view using space catalog data. But yeah, that's all I have time for today. Thanks for your attention, and I'm happy to take any questions.